How's it going, everyone? Hope you're all doing okay today. Um, I think it should be updated, but I graded your exams yesterday, um, and I apologize if I caused any confusion by opening up that test again. I had changed something to allow a different student to take the exam, and basically resulted in a situation where I could not grade any papers. So I had to reopen it for everyone. So that's why we had that confusion. So, anyway, what I plan to do, and I tried to give feedback on each of the questions that I graded. What I plan to do is sometime in the next week, I will go through and make a video basically going through the entire test and how I would suggest working those problems. That way, you can look at that and see what you did wrong if you have any questions on it. And then if you still have questions on what you did versus the grade that you receive, feel free to email me or send me a message in Canvas, and I can take a look at it. But let me know. Okay. Sorry for last Wednesday, but hopefully the video was pretty informative. That one I think was a little bit less interactive anyway, so it worked out. I think it was mainly definitions and things, but hopefully the ideas were okay too, as far as your understanding of everything. Anyway, let's continue with section 5.2 today, and then I think on Wednesday we'll look at 5.3 and 5.4. And we're moving right along, so our next test is over chapters 5 and 6. Well, maybe in 2 weeks. Not next week, but the week after, is what I'm thinking. So this next test will come up a little more. Well, it won't be more quickly. Anyway. We're barely getting started on chapter 5, though, so let's keep going. Probably 2 weeks from Wednesday, but actually it's a better estimate. Okay, section 5.2 is on the addition rule and the complements. Also, I apologize if you can hear the noise that my computer is making. It is super annoying to me. But it's my power supply. I don't know if it's going out or not, but I've ordered a replacement just to have a little peace and quiet, to be honest. Anyway, I hope it's not too noisy. It comes and goes. So, all right. So, continuing our discussion of probability, we'll look at the addition rule today, and I left off the S on complements. we'll look at the addition rule first, and then towards the end of class we'll be looking at complements and going over how to find each of these in a couple of different situations, which it turns out you'll see both of these situations on the exam, and I think it's a good way to learn it overall by looking at similar ideas but in different contexts. So anyway, before we can look at the addition rule, we have what's called the intersection of two events. In this case, when we say the intersection, this is P of A and B. This is the probability that events A and B are both successful, or they both occur. Okay. So it's the and part there that tells us it's the intersection of two events. Essentially, we want to find under what conditions would both of the events be successful or both occur. Okay. And then we want to measure the probability of that happening. And that's what P of A and B is. For example, let's say that we have a hat, and in this hat we have the numbers 1 through 10 written on folded slips of papers. Okay. And one number is drawn at random. So basically it's a random process, but we know each of the individual numbers has a 1 in 10 chance of being selected, because there's 10 different numbers and we're only selecting one of them. So this is what we call classical probability, because we know the rate at which each outcome should occur on average. So we create event A, where the result is odd. Now, if the result is odd, that means we could draw one of any 5 numbers. So as long as we draw a 1, 3, 5, 7, or 9, that means our result will be an odd number. Okay. And then we define event B. Here we say the result is a multiple of 3. For which outcomes would event B be true? What list of numbers meet this requirement that the result is a multiple of 3? Again, just the numbers 1 through 10 is what we're looking at. So if we were to draw a number at random, which slips of paper could we draw and have the result be a multiple of 3? 3, 6, and 9. Good. So as long as we draw one of those 3 numbers, then event B would be considered a success, and event B would, and so on. If for event A to be a success, we'd have to draw a 1, 3, 5, 7, or 9 to get an odd number. So the question is, if we want to know the probability of A and B, again, the way that we define probability is we calculate the number of ways it is successful, the number of ways that A and B are both successful simultaneously, divided by the number of outcomes in the sample space. Okay, the same calculation we looked at in section 1. So if we look at event A and event B, when we say A and B, we're looking at the intersection of the two events. So that means we want to find the numbers for which both events would be considered a success. So is there a single number that we could draw where event A and event B would both be successful? And then for which numbers would that be true? Three and 9, yeah. Because we look at the options in event A and we look at the options in event B, and we basically see what do they have in common. Well, they have the 3 in common and they have the 9 in common. But those are the only two numbers they have in common. So as long as we choose either a 3 or a 9, then the result would be both odd and a multiple of 3, so both events would be considered a success. Now, we look at the number of outcomes where A and B are both true. Well, that's two different numbers where that occurs. So 2 out of 10 total numbers that are possible to draw. So our probability is 2 out of 10, or 0.2. Okay. So when we talk about the intersection, we talk about the AND statement. We're looking for how many different ways are both events a success simultaneously. And that occurs if we select a 3 or a 9 in this case. So 2 different ways that both can be successes out of the 10 total options. Alright, next we look at the union of 2 events. Probability of A or B, this is the union or. This is the probability that either A or B or both are successful. So essentially, as long as at least one of the 2 events is a success, then the union of the events is a success. Okay. All right. Let's go back to our same scenarios before. We said event A was our odd numbers: 1, 3, 5, 7, and 9. And event B, this is our multiples of 3, 3, 6, and 9. So how many different numbers can we pick so that either A or B or both would be considered successes? Now, we know already from the last problem that there is some overlap. But there are some numbers that we could potentially choose from the hat where neither A nor B are successful. If we choose an 8, for instance, 8 is not odd, nor is it a multiple of 3, so it would not be a success if we chose the 8. So, which numbers could we choose and have at least one of these, if not both, be successes? 1, 3, 5, 6, 7, 9. Good. Mm-hmm. Okay. So again, let's look at that. We're saying we want all the different numbers for where A could be a success, or B could be a success, or both could be a success. And there's no need to write numbers more than one time here. So I know if we have 1, 3, 5, 7, or 9, A would be a success. And if we have 3, 6, or 9, then B would be a success. And basically, we combine those together into a single list, is really what it amounts to. So as long as we choose a 1, 3, 5, 6, 7, or 9, then at least one or the other, or both, would be considered a successful outcome. So the union is a little bit more complicated than the intersection as a result of that. Okay? It's really between these two groups of numbers, there's 6 different numbers that are possible. 1, 3, 5, 6, 7, 9. So 6 out of 10. So basically, the only thing we don't want to choose is 2, 4, 8, or 10. Because in that case, neither A nor B are successful. This one's a little bit more complicated. Let's think of this as one way and again, you don't have to do it this way. One way we could think of this is like a Venn diagram. Okay. Now, we already know that 3 and 9 are where the two groups overlap, because we already found that when we looked at the intersection. So the intersection is where the two circles overlap, 3 and 9. B also includes 6, because it's 3, 6, and 9, so we see 3, 6, and 9 are inside B. A includes 1, 3, 5, 7, 9. We already have 3 and 9 here, so let's have 1, 5, and 7 in here. And in our sample space S, the other numbers that we don't have between these two are 2, 4, 8, and 10. Okay? And so we look at that, we see 3 and 9, this is the intersection, and then the union of the two circles It's just all of these numbers that appear in either one or both circles. So 1, 3, 5, 6, 7, 9. I don't know if it's any easier to think of it that way, but that's one way we could look at it. We're not going to be using Venn diagrams, but I did want to introduce that as an alternative in this case. The other reason I like to use the Venn diagram here, at least to demonstrate it, if not, we're not going to use it like permanently. I think it helps demonstrate the addition rule next. It's okay if we weren't quite sure how to get this, because it turns out we have an addition rule that we look at. Let me write that down next. The addition rule says that P of A or B is equal to P of A plus P of B minus P of A and B. Okay, so that's just a formula, and that's a formula that I'll include on a formula sheet for this next test, whenever it is. And so let's look at that a little bit further, because we had our groups. We had A was 1, 3, 5, 7, and 9. Group or event B, we said was 3, 6, and 9. And we also already found A and B, which we said included 3 and 9. Okay. Because that's the overlap of the two, so that's A and B. So what is our probability of A? Well, we know A contains 5 outcomes where it's successful out of 10 total, so its probability is 0.5. Probability of B, there's 3 outcomes where B is successful out of 10 total outcomes possible, so 0.3. And the probability of A and B, which we already calculated, is 2 out of 10, or 0.2. So if we calculate probability of A or B, we take P of A, 0.5, plus P of B, 0.3, and subtract P of A and B, 0.2. So 0.5 plus 0.3, that makes 0.8, minus 0.2 gives us 0.6. And that's the same thing that we calculated over here. Probability of A or B is 0.6. But it comes out completely different here. The first time we did this, we were looking at it very visually, like we're actually looking at, okay, what numbers could we pick and have either one or the other or both be successful. This one is nice because it just gives us a simple formula to follow, and as long as we're able to calculate the individual probabilities, we can get the overall probability of the OR statement. Okay. So in that way, I think the addition rule is nice. Now, it may not make sense right now necessarily why the addition rule works, but let's look at that. So we took P of A plus P of B, and then we subtracted the probability of A and B, subtracted where they overlap. The reason we do that has to do with the Venn diagram. When we calculate P of A, we look at everything inside the circle A, all 5 of these numbers, And when we look at P of B, we look at everything inside of B, all three of these numbers. Okay? Because the 3 and the 9 are part of both A and B, when we took P of A and P of B, we counted these numbers twice. Okay? We counted the 3 and the 9 twice because they appear in both lists. So the reason that we end up subtracting P of A and B is that because we counted these twice, we'll take them away once, so that each number is only counting one time instead of 2 times each. Okay? So that is the logic behind the addition rule. When we add these together, we counted all 5 of these plus all 3 of these. Okay? We counted 3 twice and 9 twice. So we take away this to take away one of the 3's and one of the 9's. That way 3 and 9 are only counted one time each. We don't need to count it more than once because we're not more likely to draw a 3 or a 9. It's just that it appears in both of the lists where both are successes. So it's like we have 1, 3, 5, 7, 9, and then 3, 6, and 9, but we take away the 3 and the 9. So it's really just 1, 3, 5, 7, and 9, and then also the 6. Okay. So that is our addition rule. If it turns out that P of A and B is equal to 0, and they end up giving us 2 completely different lists of numbers, in this case, the 2 events are called mutually exclusive or disjoint. Sorry about that. And those are pretty interchangeable as far as what they reference. Basically, a disjoint means mutually exclusive, so we could use either one. Okay. So let's look at some other outcomes. And we'll go back to our numbers in the hat. So I'm going to create some new events. Event A is the multiples of 5. Yeah, sorry about that. Multiples. There's 2 L's there for some reason. I don't know what happened. Multiples of 5. Event B is the even numbers. And event C are the powers of 2. So, for which values from the numbers 1 through 10 would A be considered a success? So, basically, which numbers are multiples of 5, essentially? 5 and 10. Good. Even numbers. It's a little more straightforward. It's 2, 4, 6, 8, and 10. What about the powers of 2? Maybe one y'all are less familiar with. When we say powers, that means 2 raised to a power or 2 raised to an exponent. So if you don't get all of these, don't worry about it too much. But can anyone name some of the powers of 2? Multiples of 2 are not the same thing as power. Carson, you're on the right track. You have the 2 in the wrong place, though. Well, actually, yeah, Carson, you're thinking of the perfect squares, where 2 is the exponent. I'm saying 2 is the base. Sorry. So 2 to the first power, 2 to the second power, 2 to the third power. Two, 4, and 8. Yeah, 2 to the first power is 2, 2 squared is 4, 2 to the third power is 8. Now there's also one other that we would include, which is actually 1. 1 is 2 to the 0th power. And again, if you're not quite clear on this, whenever I give you this information on a test, I'll give you the description and the list, so you don't have to figure out one from the other. So, I mean, y'all don't have to worry about that. I'm just trying to give it some context, I guess. All right. So these 3 events, A, B, and C. What is the probability of A? How likely are we to choose a number that's a multiple of 5? One? A little bit more than that. 1 is not really an answer by itself. When we think of probability, the answer should be a number between 0 and 1, or between 0 and 100% if we use percentages. So we're saying, how likely are we to choose one of these 2 numbers from this set of 10 possible numbers? Okay. We know we could choose any of the numbers 1 through 10. How likely are we to choose a 5 or a 10 specifically? This goes back more to our discussion on last Wednesday. 20%? 0.2 or 20%? Good. Because there's a 2 out of 10 chance that we choose a number that's a multiple of 5. What about the probability of B choosing an even number? .5 or 50%. Good. And again, as I said Wednesday, I'll typically use decimals for everything. but percentages are equally correct. And then what about our probability for event C, which is to choose a power of 2? 0.4. Yeah, in each case, we know that there's 10 possible numbers we could choose, 1 through 10. So it's either 2 out of 10, 5 out of 10, or 4 out of 10. Okay, so it's just however many numbers we have here divided by 10. So we have 4 different numbers divided by 10, so 0.4. Now, A and B. First of all, we want to identify how many numbers would make both events A and B successful at the same time if we were to draw that number. Essentially, we look at the two lists of numbers and we see what do they have in common. Right, we have one number in common between the two lists, and in fact it's the number 10. So if we happen to choose a 10, that both events A and B would be considered a success, but any other number, neither one. I mean, it wouldn't be the case. So there's really only one number out of 10 where both are true. So there's a 0.1 probability that A and B occurs, the intersection. I could move it over. Anyway, what about B and C? Right there we have three numbers in common, the 2, the 4, and the 8. And so that would be 3 out of 10, or 0.3, as our probability. Yeah. So as long as we chose the 2, the 4, or the 8, both of these events would be successes. Lastly, what about A and C? Zero. Yeah. So these two events are actually mutually exclusive. There's no way that we could pick a number that's a multiple of 5 and a power of 2 at the same time, because it's either 5 or 10, or it's 1, 2, 4, and 8. There's no numbers in common between those two lists, so there's zero probability that both would be successful. Each one excludes the other from happening, so they're called mutually exclusive, or disjoint, as we said. All right. Now, if we wanted to find probability of A and B, sorry, I messed it up already, sorry, A or B, that's what I want to ask, because we already did and. Again, we can use the addition rule that says P of A plus P of B minus P of A and B. Okay? Again, that's the addition rule. Now, probability of A, we already calculated that to be 0.2. Probability of B, we calculated as 0.5. And A and B, we've calculated that probability as 0.1. So at this stage, since we've already done each piece individually, we just need to put them together to get the union statement, the OR statement. So that'd be 0.2 plus 0.5, which is 0.7. Take away 0.1, that gives us 0.6. Okay, and we would do the same for the other OR statements. If we did probability of A or C, or probability of B or C, we would take the same approach. Just plug in the values for that which we already know, and then simplify, and we'll get our answer. Okay. Next, I want to look at problem 40 on page 271. I'll go ahead and reproduce the table here. Okay. So on this table, we have parents with children under the age of 18. Well, we have families with the number of children under 18 listed. So we either have 0 children, 1 children, or 2 plus children. This is number of children under 18. And down we have who works in the household. Is it the husband, wife, or both? So I guess we're just using the traditional family setting here. Anyway. So just looking at the numbers, let me fill these in real quick because they're high. One of the nice things some of these tables do, such as this one, is they add a row and a column for the total. That saves us from some of the calculations that we have to do, which is nice. And anytime we want to organize our data, I recommend including that because it's pretty handy for anyone else who's viewing your data or your statistics. So overall, we have 1,700 families that are surveyed in this. 788 families have 0 children under the age of 18. 353 families have 1 child under the age of 18. And 559 have 2 or more children under the age of 18. Okay. In 425 of the 1,700 families, only the husband is working. In 126 families, only the wife is working. And in 1,149, both spouses are working. All right. So this is what we have. Now, based on this table, they've given us a series of questions. So part A, what is the probability that both spouses work? Now, same concept we were doing before, except instead of giving the raw data like we had with our numbers being drawn from the hat, now we have our data arranged more conveniently in a table form. Especially because we have so much data, this is much easier to work with. So, in how many couples do both spouses work? So again, we take the number that meet the requirement. So what number of families do we have where both spouses work? (1,149). And that's out of how many total families surveyed? $1,700. Good. Yeah, we know for both spouses working, that's 1,149 of the families, and the total is 1,700. So we just divide 1,149 by 1,700. I've already gotten this written down. This is 0.676. My recommendation is to round to 3 decimal places because it symbolizes rounding to the nearest tenth of a percent, which is a nice place to go to also. So it could be 0.676 or 67.6%. Okay, question B. What is the probability that a couple has one child under 18? So what two numbers would we have to divide in this case? Yeah, we have 353 couples that have exactly one child under 18, and that is out of 1,700 total families, and that comes out to be 0.208. We'll leave a little more space here. Part C, probability that a couple has 2 or more children under 18 and both spouses work. Now, this one is a little bit more, well, we could still read this from the table, but when we look at this, we say, okay, 2 or more children under 18, that's this column, okay? Both spouses working, that's this row. So in this case, if we want the intersection and of those two things, it's literally the intersection of that row in that column. 370 out of 700. 1700. Yes. That would be the 370 here, where they have 2 plus children and they both work. And that is 0.218. Okay. Does that make sense where we got the 370 from, hopefully? Okay. So for D, we want the probability that the family has 0 children under the 18, under the age of 18, or only the husband works. Now, for convenience, I'm going to call that A and B respectively. So we know probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Again, that's our addition rule. Okay. So we need probability of A, which is the probability of having 0 children under the age of 18. So for 0 children under the age of 18, how many is that? Now the 172 is something else, but we'll get to that in a second. Right now, we just want the probability that the couple has 0 children under the age of 18. Visually, the way that we would think of this is if we're just working with 0 children under the age of 18, we're just looking at this one column. Okay? Just looking at that one column. Now, so we look at the total there. So we have 788 families out of the 1700 where they have 0 children under the age of 18. Okay. Next, we look at probability of B, where B is only the husband works. So what is the probability that only the husband works in a randomly selected household? Yeah, 425 families where only the husband works out of 1700. And now A and B, we want, okay, how many families are there where they have 0 children under the age of 18 and only the husband works? What is that number? Where we have 0 under the age of 18 and only the husband works. That's our 172. Okay. So we know that 172 is the overlap, but when we say or, it's not just picking what they have in common. It's actually going through this process and using the addition rule. That way we can get everything where either the first one or the second one is true, or both. Now, we end up with these three fractions here. Now, the great thing about this is that they all have the same denominator. And we know that if we're adding or subtracting fractions, as long as the denominator is the same, we don't have to mess with it. That's our common denominator right there. So the answer will be over 1700. So we need to take 788 plus 425 minus 172. We'll combine the three numerators together. That comes out to be 1041. And then we divide, and we get a probability of 0.612. Okay. The main thing we want to do anytime we have the OR statement is go ahead and apply the addition rule and make sure we find each piece individually before we go ahead and combine everything together. So we looked at the probability that a couple had 0 children under the age of 18, the probability that in a couple only the husband worked, and the probability where both were true, no children under 18 and the husband was working. Only the husband was working. Alright. There is one last question here. Let me use this margin over here to answer that, or ask that. And E says, is it unusual to say only the wife, is it unusual that only the wife works? I feel like I'm not saying that correctly. Is it unusual for only the wife to be working? Well, first thing we want to do there is figure out the probability of that occurring based on this research. And how many of these families is only the wife working? $126, right. So that's 126 out of 1700. And that comes out to be 0.074. Now, the way that we talked a little bit about something being called unusual in section 1, and we defined unusual to mean less than 5% chance. So, is this less than 5%? Well, what percent is 0.074? That's probably a better question. If we took the decimal 0.074 and translated that into a percentage, that would be 7.4%. So is it less than 5%? No. So not unusual. So that's our statistical definition of unusual. I mean, it's still not something that happens a whole lot because, like we see over here, it's only 7.4% of the time. But it is considered unusual. Well, it's not considered unusual. I just lost track of what I was saying. I'm sorry. It doesn't happen very often, but not to the point where we would consider it unusual. I guess that's the better way of what I was trying to say. Anyway. So, that's two different ways right there that we see the and the or statements and all the different probability things that we talked about presented. Sometimes we're just given the basic information, like we had numbers 1 through 10 in a hat, and we're just picking one at random. And what is the probability of this, this, and this happening? Okay, and then other times we have a whole lot of data that's been collected and arranged nicely into a table for us. And then we can read information from this table now and draw conclusions from there. And make our calculations like we saw. Okay. So that takes care of the addition rule. And let's move forward to complementary events. This is the other topic we'll cover today. It's shorter, so that's good. Okay, now, first of all, I want to stress that this is complementary with an E and not an I. That means that we're not saying nice things about the events, or they're not free events. Complementary in this scenario with the E means that it's based on the Latin root that means to fill. It's basically a complement of an event fills in what's missing, and that's probably the best way of expressing that. But let me go ahead and write down our definition. Suppose we have an event E. One, its complement is written E, and then we have a C kind of written as an exponent almost. We call it a superscript. So it'd be E complement, so EC. And 2, E complement is the list of outcomes that are not already included in event E. Okay. E complement is the outcomes that are not already included in E. So we go back to our hat, just for simplicity's sake, really. And we said before, event A we defined as the numbers 5 and 10. That's the multiples of 5. Event B we had called the even numbers 2, 4, 6, 8, and 10. And event C was the powers of 2, which was 1, 2, 4, and 8. So based on that, what is a complement? What outcomes would be part of a complement? So the complement is the outcomes that are not already included in the original event. So if event A has 5 and 10, what would event A complement include? Okay. So we say when we look at the complement, it is the outcomes that are not already included in E. Good. Good, that was it. Okay, so if A has 5 and 10, then A complement would have all the other numbers from 1 to 10 except 5 and 10. So 1, 2, 3, 4, 6, 7, 8, and 9. What about B complement in that case? One, 3, 5, 7, 9. Good. This one's a little more clear cut as far as how we would define it. Yeah, we would, since B is the even numbers, then B complement would be the odd numbers. Exactly. That one we at least have a definition for. C complement, which is kind of a weird thing to write. C contains 1 and 2, so we'll put 3 over here. C contains 4, 5, 6, and 7. C contains 8, and then we'll put 9 and 10 over here. So between the two of them, we have all 10 numbers. So 1, 2, 4, 8 are here, and the other numbers, 3, 5, 6, 7, 9, and 10 are here. And that's always going to be true. Whatever, so we know the sample space is 1 through 10, so whichever numbers are not here, they're going to be over here. Okay. Same thing for each of these. Now our probability of A, we said it was 2 out of 10, or 0.2. Our probability of B, we said it was 5 out of 10, or 0.5. And our probability of C is 4 out of 10, or 0.4. We already calculated those before. What about the probability of A complement? .8, good. Probability of B complement, well, we have 5 numbers, so it would be 0.5. And the probability of C complement, we have 6 numbers, so 0.6. Now, look at the probability of A and probability of A complement, 0.2 and 0.8. Probability of B complement, 0.5 and 0.5, and the probability of C and the probability of C complement, 0.4 and 0.6. What seems to be true for each pair of event and complement? What seems to be true about probability of A and probability of A complement, as well as for B and B complement and C complement? They all add up to 1. Exactly. 0.2 plus 0.8 is 1, 0.5 plus 0.5 is 1, and 0.4 plus 0.6 is 1. That's because we had 10 numbers total that are possible, and so whichever ones are here, the other ones are here. So between them, all 10 numbers are either in this first list or the second list. And that's the same true for all of the events. For B, again, we have 5 of them here, so the other 5 are over here. And for C, we have 4 of them here, so the other 6 are over here. So between them, we've covered every single value of those 10, and therefore it represents 100% of the probability, or 1 in this case, that they add up to. So that leads to what we call our complement rule. And the complement rule says, well, let me write that down first. Probability of E plus the probability of E complement is equal to 1. And that's true for any event E. If we add the probability of E and the probability of its complement, it's always going to equal 1. Now, with manipulation of terms here, we could also create a second formula, which is the probability of E complement is 1 minus the probability of E. Okay? So that means if we already know the probability of E is 0.7, then we take that away from 1, so the probability of its complement must be 0.3. So that's the kind of thing that we can use that for. Now we're going to come back to this complement and use it a little bit more later. So we just want to introduce the basics here in this section. Let me go ahead and give you your homework. This is on page 269. So go ahead and look at those. When I say 5 through 13, all that means also the even numbers there, but that's 5 through 12, I believe, are working with like a similar thing as what we talked about with our numbers in the hat. They did it a little bit differently, but same concept. I forget what the others are. So it's all based on the same thing that we've been talking about. Anyway, so I think that's enough for today. We're just about out of time anyway, so it works out. Hope everyone's had a good day, or will have a good day that we're out of class. Maybe not just mine, but your others. Anyway, enjoy the rest of your day, and we will continue this on Wednesday. And again, be sure you look at your test and look over the comments I left you. If you do have any questions over grading, let me know. And, like I said, I will go back and make another video later this week, I don't know exactly when, where I go over how to do each of the problems on the test. That way, if you do have a specific question over one of the numbers, you just want to know how to work that problem, I'll go ahead and upload that and link it as such, so that you can get on that, and you can skip around whatever problems you need to look at. So anyway, I thought overall we did pretty good on the exam. I know a few of you didn't do quite as well as you might have hoped, which is fine. It's still recoverable at this point. Just make sure you keep up with everything. But a lot of you did really well, which is also good to see. So anyway, you all take care, and I'll see you next time. Bye.